Hello and welcome to another WJEC A level physics question. This is question 7 from June 2012's Unit 4 paper, and it's a question on basically planetary orbits and Kepler's laws, and this sort of work is still in Unit 4. So we're given a table for Earth and Jupiter, given the mean radius of their planetary orbits and their orbital periods. And first of all, we're asked to state Kepler's 3 laws of planetary motion. It's important that we do learn these. So the first law tells us that the planets orbit the Sun in elliptical orbits with the Sun at one focus. The second law, this one tells us basically that a line between a planet and the Sun sweeps out equal areas in equal times. And a third law is that the orbital period squared is directly proportional to the cube of the mean orbital radius. Okay, so make sure you learn those. Okay, next part of the question asks us to show that the data above are consistent with Kepler's third law. Well, Kepler's third law can be expressed in the form that t squared is proportional to r cubed, or t squared is equal to a constant times r cubed, or even r cubed equals a constant times t squared. But the way I've written it, we can say that the constant k would be t squared over r cubed. So let's look at Earth first of all. Let's put in the values, and because we're just going to be comparing the constants to see if they're near enough the same for both planets, we don't need to convert years into seconds or anything. So for the Earth, we've got 1 year squared over 149.6 times 10 to the 9 meters cubed. So if we put those values into the calculator, what are we going to get? We get basically 2.99 times 10 to the minus 34 years squared per meter cubed. Let's take the values for Jupiter. K will be 11.86 squared over 778.6 times 10 to the 9 cubed, so let's put that one in. And that will give us 2.98 times 10 to the minus 34. So you can see that both of those constants are very, very close to each other. So this basically verifies Kepler's law. So let's just put a little comment. Constants are almost equal. Verifying the third law. Bit of a big gap there. Next, a question asks us to explain what's meant by centripetal acceleration. So this is just simply acceleration towards the center of a circle. And last bit, we've got to calculate the mass of the Sun. So what we should do here is a standard setup for orbit type questions. We're going to equate the gravitational force of attraction between the Sun and one of the planets, which is gm1m2 over r squared, to the centripetal force m2v squared over r, where m2 here is going to represent the mass of the planet that we're interested in, and m1 is going to represent the mass of the Sun. So we can do a little bit of cancelling. We can cancel one of the r's on both sides, and we can cancel out the m2's, and we end up with g m1 over r is equal to v squared. But v is 2 pi r over t. 2 pi r is the circumference of the orbit, the distance travelled in the orbit in a time t. So what we've got next is gm1 over r is 4 pi squared r squared over t squared. We're trying to find the mass of the Sun, which is m1. So m1 is going to be 4 pi squared r cubed. This r is going to come up to the top on the right hand side to become r cubed over t squared and big G. So we could try this with either of the pieces of data, but let's use the Earth. So we've got 4 pi squared times 149.6 times 10 to the 9 cubed over t. Now t here we can't leave in years, we've got to turn it into seconds. So what we've got is 365, or 365 and a quarter if you like, times 24 hours times 60 minutes and 60 seconds squared times 6.67 times 10 to the minus 11 for the universal gravitational constants. So give me a minute to put that into the calculator. Almost done. And we end up with 1.99. I'll go with 1.993 just because the data originally was 4 significant figures, times 10 to the 30 kilograms, which is something that is about right. From sort of general knowledge, some people already know that the mass of the Sun is roughly 2 times 10 to the 30 kilograms. So thank you very much for listening. Please remember to like and subscribe, and feel free to add any questions to this video. Goodbye.